Ever wondered what it would be like if your programming environment wasn't just a cold, static text editor, but instead maybe a living, breathing universe of interconnected objects you could really interact with? Imagine like sculpting code, watching it respond instantly, rather than just typing it out and hoping for the best. Today, we're taking a deep dive into the fascinating world of Squeak Smalltalk, and we'll be drawing on insights from Squeak by example. Our mission, really, is to uncover the unique philosophy and the powerful tools that make Squeak such a standout in the programming landscape. We're looking for those moments, those aha, things that might just change how you think about software development, offering a fresh perspective on what coding can actually be.
Absolutely. Smalltalk's approach is profoundly different from many conventional languages you might already know. It's an environment built fundamentally on this principle that everything is an object. And that simple, elegant idea and unfolds into this incredibly dynamic and interactive experience. It really blurs the lines between, development and execution.
Okay, let's unpack that. This world of live objects. For someone who's maybe used to working with separate files, compiling, then running, what does this direct, continuous interaction in Squeak actually feel like?
Well, what's truly fascinating here is the concept of direct manipulation at every level, especially through its graphical interface, which is called morphic. Think about your typical UI development. You design it, you code it, then you run it, right? See if it works. In Squeak, there's no hard distinction between composing and running the interface.
Hmm.
It's all live. You can literally interact with and reconfigure UI elements on the screen while your program is running. For instance, the book describes how you can blue-click a menu item, drag it away from its parent menu, and instantly it becomes an independent clickable button right there on your screen.
Wow, just like that.
Just like that. You haven't touched the code, haven't recompiled anything. You've just reshaped your running application's UI on the fly. This really highlights the directness and liveness of the system. The shapes on your screen are the objects you can examine and change.
That's a truly, paradigm shifting idea, a UI you can reshape in real time. Does this liveness extend beyond the interface? What about the core logic? How do you understand what's happening inside your running gun in such a fluid environment?
Oh, absolutely. That direct access is everywhere. Squeak offers tools like the Inspector and the Explorer. They're essentially live windows onto the internals of any object in your system.
Like looking under the hood while the engine's running.
Exactly. Instead of setting breakpoints and sort of guessing what values might be, you can, for example, type timestamp now into a workspace. Okay. Then just inspect it with a quick keyboard shortcut, CMDI, I think. And what you get isn't some static snapshot. It's a live view into that precise timestamp object. You see its exact instance variables, their current values, even its class. The Explorer then takes it a step further. It lets you visually navigate these deeply nested object structures. It's like, opening up a complex machine and poking around inside while it's still running, seeing all the gears and connections moving. It's an incredibly intuitive way to build up mental models of complex systems,
That's a powerful way to visualize what's actually happening. Okay.
Yeah.
But what about when things go wrong? We all know they do. Most debuggers are great for looking at what was, a post-mortem. How does Squeak's debugger let you interact with the present state to not just understand, but maybe fix issues right then and there?
Yeah, this is where Squeak's live nature really, really shines. The debugger isn't just a passive observer. When an error happens, it doesn't just show you the runtime stack, it brings your entire application to a halt, right in that exact state.
Okay.
You can then inspect any object, navigate the call stack like you'd expect. But here's the kicker.
Yeah.
You can modify the source code right within the debugger.
Seriously, change the code while it's paused.
Yep. Find the bug, change the line. And once you've made a fix, you can simply continue executing your program from that modified point.
Without restarting.
Without restarting. Imagine you've got a bug deep inside some calculation that only shows up after, say, several minutes of processing. In a conventional environment, you change the code, recompile, restart the whole process, wait again. It's frustrating.
Tell me about it.
In Squeak, you step into the debugger, you identify the issue, you correct the faulty line right there, and you just hit proceed. It radically changes the debugging workflow, makes it incredibly agile, minimizes those long feedback loops. It turns debugging into this live interactive problem-solving session instead of a forensic investigation after the fact.
Okay, so this philosophy of live objects and direct interaction, it runs incredibly deep. But what does this mean for how you actually write the code? Is it just different syntax, or is there a fundamental shift in how you construct programs from the ground up?
Well, if we connect this to the bigger picture, Smalltalk's core belief is this absolute uniformity. Everything is an object, and everything happens by message sends. Now, that isn't just some catchy phrase. It's a foundational principle that truly permeates the entire system. When you write code, you are always sending messages to objects. Always. Even classes themselves are objects. They're instances of unique metaclasses.
Metaclasses. Okay, go on.
Think of it like this. If an object is a house, right? A class is the blueprint for that house.
Got it.
A metaclass, well, that's the blueprint for blueprints.
Ah, okay. Blueprint for blueprints. I like that.
It's a powerful, kind of recursive idea. It makes the system incredibly self-describing and flexible. You can even modify how classes behave, not just instances. It's pretty mind-bending.
That really makes metaclasses click. So, okay, if everything is a message send, what kinds of messages are we talking about? Does it follow standard patterns?
It's actually surprisingly simple at its base. There are just 3 kinds of messages in Smalltalk. First, you have unary messages. They take no arguments, like 1 factorial. Then, binary messages. They take exactly 1 argument, like 1 plus 2.
Right.
And finally, keyword messages. These take an arbitrary number of arguments, indicated by keywords, like 2 raised 2, 6 modulo 10.
Raised to and modulo being the keywords.
Exactly. Those simple rules, though, they have some profound implications, particularly for evaluation order. Here's a fun one, often surprising for people coming from other languages. 1 plus 2, 3 in Smalltalk. It evaluates to 9.
9, not 7.
Nope, 9. Because binary messages of the same kind are evaluated strictly left to right. There's no operator precedence like in traditional math.
Whoa.
So 1 plus 2 evaluates first to 3, and then 3 evaluates to 9.
So you have to use parentheses if you want the multiplication first.
Precisely. 1 plus 2, 3 would give you 7. It simplifies parsing for the machine, but yeah, it definitely means you have to unlearn some ingrained habits. No more PEMDAS debates. Smalltalk keeps it simple.
That's definitely a brain teaser, a truly unique twist. Okay, but if everything is a message, and there are no traditional operators or keywords for control flow, how does Smalltalk handle fundamental things like if statements or for loops?
Right, that's a really important question. How does such a uniform object model handle these common constructs? Well, Smalltalk doesn't have dedicated syntax for them. No special if keyword, no for keyword. Instead, these are also expressed by sending messages, usually messages to objects like billions or collections. And these messages take blocks as arguments.
Blocks, like closures.
Exactly. Blocks are essentially first-class objects, technically lexical closures. They represent a chunk of code, a function, basically. So, for example, a conditional is just a message sent to a Boolean object. You write 1, 2 if true, bigger if false.
Smaller false.
Is the message. Yeah, sent to the Boolean result of 1, 2, which is false. And the arguments are these blocks, the code inside the square brackets. The Boolean object itself knows how to execute the correct block.
Clever. And loops. Similar idea. Iteration messages like collect dot select dot or inject dot into are sent to collections. They take blocks to define their behavior. You might send a collection, each assertion to transform every element into a string, the block. Each asterisk gets executed for each element. It's incredibly powerful because these blocks can capture and use variables from their surrounding context. Huge flexibility.
So bringing this all together, it means even your control flow isn't some rigid language construct bolted on. It's just another elegant dance of objects sending messages to other objects, in this case, blocks. It sounds incredibly powerful and flexible, very expressive. Okay, so in this dynamic object-centric world where code is live and everything's an object sending messages, how do developers actually structure their applications and collaborate effectively? What are the implications for software design principles? And, things like version control. Yeah, the object model definitely extends into design patterns, and it's in pretty interesting ways. With some subtle but significant differences from other OCO languages, Smalltalk enforces strong encapsulation, but its definition is perhaps a bit tighter. Instance variables are strictly private to the instance itself.
Not just the class.
Right, not the class. This is different from languages like Java or C++C, where other instances of the same class can often access each other's private variables directly. In Smalltalk, 2 instances of, say, point can't just grab each other's X and Y variables. They have to use accessor methods. It really pushes you towards cleaner object interfaces.
Interesting distinction. What about method lookup, inheritance?
Method lookup also has its nuances. A self-send triggers a dynamic lookup starting from the receiver's class, just like you'd probably expect. But a supersend, that triggers a static lookup. It starts searching from the superclass of the method where the supersend occurs. not necessarily the immediate superclass of the object receiving the message.
Say that again. Static lookup from where the super is written.
Exactly. This is crucial because it ensures that when you override a method, your supercall always reliably invokes the original behavior from the specific superclass where that method was defined, even if other classes in between have also overridden it. It avoids some subtle bugs you can get in other inheritance models and provides really predictable behavior when you're composing inherited functionality. That's why, for instance, the convention is that your initialize method should always start with super initialize to make sure all the inherited state gets set up correctly, step by step up the chain.
Okay, so the uniformity of the object model really drives both encapsulation and how inheritance works in this very specific, powerful way. Makes sense. What about ensuring code quality and enabling collaboration? In this living, evolving system, how do developers keep things coherent and, well, shareable?
Right, for code quality, testing is absolutely paramount. And Squeak provides Unit, which is a really robust unit testing framework. In fact, Unit was the inspiration for many of the other XUnit frameworks you see today, like JUnit.
Oh, really? It started there.
Pretty much. The book strongly emphasizes writing tests before the code TDD, test-driven development. That's very much part of the culture. Good unit tests are repeatable. They run without needing a human to check things. They tell a clear story about one specific piece of functionality. And ideally, they change less often than the code they're testing. What makes Unit particularly effective in Squeak's live environment is the immediate visual feedback. You run your tests.
And you get the green bar?
You get the green bar for passes, yeah.
But
Or yellow for failures, red for actual errors during the test run. That instant visual cue gives you incredible confidence. You can refactor rapidly, develop quickly, knowing your existing functionality is still sound. Run tests, get green, move on.
that tight feedback loop again.
Exactly. And for sharing code, Squeak uses something called Monticello. It's a truly unique distributed version control system designed specifically for Squeak's object-centric world.
Not like Git or SVN then.
Not really. Unlike traditional systems that track changes in text files, Monticello manages packages. Think of a package as a group of class categories and method protocols. It versions these as .mczs files, which are basically zip-compressed bundles of the actual live objects and their changes.
So you're versioning the objects, not just the text.
Precisely. You're tracking and sharing changes to the objects themselves, their structure, their methods, and a really powerful feature is something called extension methods. This allows you to add methods to classes that belong to other packages. So maybe you want an as-equal method on the base object class. Monticello lets you define that method, but track it as part of your package without having to modify the original core object package.
Ah, that avoids merge conflicts and lets you extend things cleanly.
Totally. It's incredibly flexible for customizing and extending functionality without stepping on toes. Then there's Squeak Source, which is basically a web platform, kind of like GitHub or GitLab, but specifically for hosting these Monticello repositories. Makes collaboration and sharing pretty streamlined.
So wow, it sounds like even version control is deeply integrated into this live environment, designed specifically for managing packages of living, evolving code, rather than just static text files. It really is a completely holistic approach. We've journeyed through Squeak's truly unique approach to software development then, from its live, interactive environment, that direct manipulation of the UI, to its foundational philosophy where everything, literally everything, is an object sending messages. We've seen how this leads to really elegant solutions for things like control flow using first-class blocks, and these robust integrated tools for testing with Sunit's green bar and sharing code with Monticello.
Yeah, this deep dive, it really shows that programming doesn't have to be confined to static text files and these rigid compilation steps we often take for granted. Squeak offers this compelling vision where you're constantly interacting with molding, evolving a live system. It's really an invitation to think about software less like a rigid blueprint that you painstakingly translate, and maybe more like a dynamic, responsive organism that you're cultivating and interacting with in real time.
So here's a thought to leave you with. What if the future of programming looked less like writing static scripts and more like sculpting and evolving a living, interactive system that responds directly to your touch? We definitely encourage you to explore Squeak Smalltalk. This sounds intriguing. See how this alternative paradigm might spark some new ideas for your own coding journey. Until next time, keep diving deep.